In this video right here, I'm going to be running through problem 4 of chapter 16.5 on the Chemwiki. So this is acid-base titrations, and they're asking you to find the pH of the following solutions. So part A, you have 100 milliliters of 0.105 molar hydrochloric acid and 100 milliliters of 0.115 sodium acetate. So first thing we're going to want to do is calculate the new molarities, because since we mix these together, there's a new total volume but the same number of moles. So your molarity is going to change. So the way we do that is you have this formula, M1V1 equals M2V2. So we have 0.105 molarity times 100 milliliters equals M2, which is our unknown, times 200 milliliters. So when you solve that, you get M2 equals I should have this. Where is it? 1 second. It equals 0.0525. 0.0525 moles per liter. So that's your concentration for your H plus ions, because your concentration of hydrochloric acid is going to equal your H plus concentration because it's a strong acid, so it fully dissociates. Anyways, moving on. When you do the same thing again for your sodium acetate, we're just going to look at the acetate concentration because for the same reasons they are equal. That is going to equal 0.0575. Okay, so now we're going to need the Kb for acetate, because it's the conjugate base of acetic acid. So the Ka equals 1.8 times 10 to the negative 5th. And to get the Kb, you take 1.0 times 10 to the negative 4th and divide 14th, not 14th, and divide that by the Ka, which is going to be 5.56 times 10 to the negative 10th. So you see a lot of people write ice tables, but in this situation you have a Kb so small that your initial concentrations are not going to be affected. So your actual equation is going to be really simple. So that's when you plug it in. But first, general formula is going to be HC2H3O2 concentration over H plus and acetate ion concentration. So then we plug things in. We get 5.56 times 10 to the negative 10th equals X, which is the concentration for the HC2H3O2, which is it's going to be our unknown, over your H plus concentration, which is 0.0525 times 0.0575. So you don't have to write in a minus X here because X is going to be so small that it's not going to affect it. So when you solve for X, you get X equals 1.458 times 10 to the negative 12th. And you take the negative log of X, that's going to give you your pH. So 1.28 is going to be your pH. There you go. That's problem 4. Pretty simple. Alright, moving on to part B. Part B is similar. We have 50 milliliters of hydrochloric acid, 0.10 molar. Basically, they just switched up the molarities and the volumes. So once again, we're going to use the same Kb, and we're going to find our acetate concentration and our H plus concentration because they changed. So your new acetate concentration is going to be 0.10 molar, and your new H plus concentration is going to be 0.0333, repeating, molar. And so we're going to do the same thing again. Use your Kb and just plug and chug. So when you basically just follow the same process as up here to cut down time, I'm just going to write in the answer because I'm sure you guys are smart enough to figure it out. X equals 1.85 times 10 to the negative 12th molarity. And so you take the negative log of that, and you get a pH equals to 1.477. So, moving on to part C. Part C is a little bit different. now you're using different solutions. So you have 100 milliliters of 0.109 molar acetic acid again, but instead of putting it into an acid, this time you're putting it into 100 milliliters of 0.118 molar sodium hydroxide, which is a strong base. So just as with the HCl, your concentration of hydroxide, this guy, is going to equal the concentration of sodium hydroxide. So you do your M1V1 equation to get your new molarity with the combined equation. So your concentration of OH minus is going to be equal to 0.059, and then your acetate concentration is going to be 0.0545. H3O2, or this is HC2H2O, equals 0.0545. So we're going to do the Ka for acetic acid, and your Ka is going to equal that acetate ion times your H plus ion divided by your acetic acid. So right here you got to be careful, because this H plus, there's already going to be H plus in the solution, and the way we're going to find out how much H plus is in the solution is by using the auto-ionization of water. So if you take 1.0 times 10 to the negative 14th and then divide it by your concentration of OH minus, you're going to get your concentration of H plus, which is going to equal 1.695 times 10 to the negative 13th. Okay, so now when we plug things in, we can't just make the assumption that the H plus concentration is not going to be changed because it's so small of a number. So we're going to have to add an X term into here, which is going to make things a little more complicated. Still, it's not that hard of a problem, as long as you understand what's actually happening. It can be really confusing, but the basics of it are not that hard. And you're going to repeat this over and over again with freezing constants and a lot of other things. So your Ka, which is 1.8 times 10 to the negative 5th, is going to equal X times 1.695 times 10 to the negative 13th plus X. Remember I said we're going to have to add an X term, over 0.0545. You should actually write out your units. I'm kind of lazy, so I don't. But if you're on a test, you should really write it. It keeps you from making a lot of mistakes. So solve for X. You just got to expand it and then use the quadratic formula. You get X to equal 9.9045 times 10 to the negative 4th. So now that is going to be the amount added to your H plus concentration. But since this is so small, it's 10 to the negative 13th, you can just kind of ignore that part. So that we're going to call that our concentration. So you take the negative log, or well, okay, first off, before I do that, we have to find out your new OH concentration. So your OH minus plus your H plus is going to go to water. So if you take your OH concentration, which is 0.059, and subtract this guy, 9.905 times 10 to the negative 4th, you're going to get your new OH concentration. So that new OH concentration is going to be 0.058. It's a very small change. And take the negative log of that, will give you your POH, which is, so your POH is going to equal 1.237. And then if you subtract 14 from your POH, you can't see that. Let me move that down. All right, if you subtract your POH from 14, you're going to get your pH, which is 12.763. All right, there we go. Moving on to part D. On the other side. All right, part D. Once again, it's similar to part C. So we have 100 milliliters of 0.998 molar acetic plus 50 milliliters of 0.110 molar sodium hydroxide. Alright, so we're going to do the same things. First, we're going to calculate our OH minus concentration, which is going to be 0.03667. You can rewind it and check how I did it in the other ones if you want to look at that. H plus is going to be 2.73 times 10 to the negative 13th. We're going to plug it into that same Ka again, which is Ka equals H plus times C2H3O2 minus over acetic acid. And so we plug in our values, we get 1.8 times 10 to the negative 5th equals 2.73 times 10 to the negative 13th, which is our H plus concentration, plus X, because once again, as in the last one, you need to include this because 2.73 is a very low number. So that times X, that plus X times X again for your acetate ion over 0.6653, which is your acetic acid concentration. You can calculate that if you want to, but just to check my math, but I'm pretty sure that's right. Anyways, solve for X equals 0.00346. Do the same thing, take our OH minus, which is 0.03667, subtract 0.0346 from that, and you get 0.0332. Take the negative log of that, you get your POH. POH equals 1.48, which means your pH equals 12.52. Alright, there you go. That should help. Yeah, go back through it if you need another explanation. Thanks for listening.